Hello, everyone. In this lecture, we're going to introduce a new set of special functions and work to try and understand their properties. These functions that we'll focus on today are referred to as the hyperbolic trigonometric functions. And you'll see where the trigonometric part comes from because they bear a significant resemblance to the trigonometric functions we already work with, such as sine or cosine or tangent or some of the inverse functions as well. And over this lecture and the next one, we're going to introduce the initial definitions of these functions and discuss their more calculus theoretic aspects, such as the derivatives and their integrals. But on top of that, we'll see that these functions have similar identities to the usual trigonometric identities that you've seen for, say, sine and cosine. And in the video that follows this, we're going to introduce the inverses of these trigonometric functions and similarly look at their properties, primarily these calculus theoretic properties, again, such as the derivative and the integral. So let's jump right into it. Let me show you what I want to talk about today. So the first inverse, or the first hyperbolic trigonometric function we're going to look at is called sinc. So this is the hyperbolic sine function. So hyperbolic sine. And in this case, we write it as sine h. The h denotes that it's a hyperbolic function. As I said out loud, we refer to this as the sinh function. So we really emphasize the h on the end there, and we blend it with a ch sound. So it's like sin of x, but it's sinh of x. And this is a more formal definition than just writing sin h of x. In fact, this is determined entirely in terms of exponential functions. So sinh of x is really just a shorthand for 1/2 of e to the x minus e to the minus x. So let's think about what this thing looks like. Here we have the x-axis, the y-axis. In our case, you can see that sinh of 0 is equal to 0 because you get 1 minus 1 on the numerator of this function. And as x gets really large and positive, the e to the minus x term disappears. It goes to 0. And so you're really just left with e to the x over 2. You can try it with your calculator. Put in x is equal to 1,000 or then 10,000 or 100,000 or even 1,000,000. And you'll see that this function looks more and more like just a regular exponential. Similarly, as x gets negative, the e to the x term disappears and the e to the minus x term takes over. So what you essentially get is something that could potentially, if you don't label your axes, be confused with x cubed. Similar to x cubed, this is an odd function. You can check that yourself. It goes through x equal to 0. But now the growth here is exponential. It's not polynomial. So if you put in x equal to 1,000 to x cubed, that number is going to be much smaller than what sinh of 1,000 is equal to. Now, since we've defined the analog of the sine function, let's think about the cosine function as well. So let's say the hyperbolic, and I'll put it in quotes again, cosine. Well, again, we have a nice symbol for this, C-O-S-H. We pronounce this cosh of x. So again, we're emphasizing the h for hyperbolic here. And this is just a short form for a regular exponential function that looks like this. So e to the x plus e to the minus x over 2. Look at the difference between these functions. Really, the only difference is the minus or a plus in the middle of these two exponential terms. And so what this tells us, we can use the same sort of ideas for sketching that we used for the sinh function. And we see that when x is equal to 0, this thing actually goes through 1. And Again, if you don't label your axes nicely, you might be under the impression that this thing kind of looks like x squared maybe, or x to the 4. I suppose it would have to be x squared plus 1 technically. But again, these are exponential functions. They grow much faster than polynomial functions. In fact, they grow faster than any polynomial function. But like x squared or x to the 4, this is an even function, right? It has that nice symmetry over the y-axis. And so just like your regular trigonometric functions, you can use these base hyperbolic sine and hyperbolic cosine in order to define a plethora of other functions. So of course, the first one that would come to mind is a hyperbolic tangent function. So let's say the hyperbolic tangent is tanh. And in this case, it's defined in the same way as tan is. It's hyperbolic secant divided by hyperbolic cosine. And if you use the exponential definitions here, you get e to the x minus e to the minus x. And similarly, you get e to the x plus e to the minus x. So if we offer up a brief little sketch here of what this one looks like, we get an x here, we get a y here. Well, in this case, we can see that as x goes to infinity, the limit here is going to be 1 because those e to the x terms become dominant, and you get e to the x over e to the x in this quotient here. Similarly, as x goes to minus infinity, the e to the minus x's become dominant, and the quotient becomes -1, coming from the negative on the top. So you have a horizontal asymptote. So I will write this on my diagram. So y is equal to 1, and y is equal to -1. And so my hyperbolic tangent function, similar to the usual tangent function, it's an odd function, and it's a steady increasing function that goes through 0. So just like with the trigonometric functions, I have tangent and I also have cotangent. That is cosine over sine. So in this case, you have this COTH. I don't think I've ever heard anyone say this out loud, coth, potentially. But again, I don't think anyone's ever said it out loud around me. So this is cosine, hyperbolic cosine divided by hyperbolic sine. And essentially, you just flip the fraction for the tanh function. And in this case, now you can see that what was a 0 for the hyperbolic tangent becomes an asymptote, whereas you still get these horizontal asymptotes of approaching 1 as x goes to plus infinity and -1 as x goes to minus infinity. And so you get something that looks like this. So it's sort of lying in the regions where the tangent can't reach. Okay, so kind of like a 1 over x function. Again, if we're just sort of thinking about these things visually without putting any actual numbers on the graph, you can think of it a little bit in that way. Okay, then of course there's two other main hyperbolic trigonometric functions that you can define. The first of which is the secant function. So this is sec of x. This is hyperbolic secant. This is given by 1 over cosh of x, which if you take your cosh function with the exponentials, the 2 now goes on the top because you're inverting the fraction, and you get e to the x plus e to the minus x. And in this case, what you can find is that your function approaches 0 as x goes to plus or minus infinity. And in fact, it just has a little tiny bump at +1 when x is equal to 0. So there might be this point on the graph, 0, 1, and everything else is just, it kind of looks like a little bell curve function. So this would be y is equal to, sec of x. And of course, that leaves us exactly one more, and that will be cosec. Again, another one that I don't think I've ever heard anybody say out loud, but it's the analog of the cosecant, and the hyperbolic cosecant here, which is 1 over sinh of x, which is equal to 2 over e to the x minus e to the minus x. And that root, that 0 of your sinh function now becomes an asymptote. And again, you get something that kind of looks like a 1 over x function. So I'll put it on the same graph. Hopefully it doesn't make this too cluttered, but you have this property right here. And this is going to run through what I already have written. But nonetheless, it's not pretty. I hope that everybody gets the idea of what I'm trying to say here. Again, I highly recommend maybe pausing the video and typing these things into maybe Desmos or another one of these plotters so that you can get a much better picture than just my rough little sketches. But the cool thing about these hyperbolic trigonometric functions is that they similarly satisfy identities. So for example, let me show you one. If I take 2 times sinh x cosh x, well, now what I can do is I can use the definition of sinh and cos. So the sinh becomes e to the x minus e to the minus x over 2. And then the cosh becomes e to the x plus e to the minus x over 2. So similar how maybe if you were in high school, you learned maybe sine and cosine rise over run, and you can use these in the Pythagorean rule to get different identities for the regular trigonometric functions. You can just use the definition of these hyperbolic trigonometric functions in order to derive identities. So clearly, right off the bat, one of these twos is going to be canceled. So I get one of them is left. I'll kick it out front. And now this is a difference of squares problem. This is a factored difference of squares. So when I turn this into a difference of squares, I get e to the 2x, that's e to the x and then all squared, minus e to the minus 2x, that's e to the minus x and then all squared. So this is a difference of squares problem. But what is this? This is just, if I scroll back for a second, that's my sinh of x function with x replaced by 2x. So now it's just a composition, pardon me, and this gives you sinh of x, sinh of 2x. So this is a double angle formula. Remember that there's trigonometric identities that tell you sine of 2x is equal to some product of sine and cosines. I can't remember off the top of my head. This is the analog of that. This is a double angle formula. It says sinh of 2x is 2 sinh of x cosh of x. And so let me list these off for you. You can similarly prove them in the same way that I just did above. So the first one that I'll give you is the one that I just proved. The rest of them will not be proven. I highly recommend trying to prove them on your own, partially because it shows that you understand these hyperbolic trigonometric functions, but partially just because it's kind of fun. I used to love proving trigonometric identities because it's a sort of rewarding and simple exercise in problem solving and in calculus. Now, this is the weird one that takes a little bit of getting used to. This is the version of the Pythagorean identity that you know from trigonometric functions, right? So sine squared plus cos squared is equal to 1. Well, in this case, you get cosh squared minus sinh squared is equal to 1, right? So the big difference here is that minus sign now. Okay, let's take a look at another one. I gave you the double angle formula for sinh. Now let me give you the double angle formula for cosh. And this is actually what you would probably confuse with the Pythagorean identity. So if you were to add cosh squared and sinh squared. In fact, what you would be getting is cosh of 2x. So that's the double angle formula for this. So it's a little weird, right? These things, they're not exactly trigonometric functions. They have slightly different properties, and that makes them a little quirkier and a little harder to get used to. Similarly, we can get rid of squares. So if I have cosh squared, this is the same as cosh of 2x plus 1, all divided by 2. Similarly, if I take sinh and I square it, this gives me cosh of 2x minus 1 now, divided by 2. Again, I highly recommend trying to prove these on your own and seeing where they come from. We remember that there's a version of the Pythagorean identity in terms of tan and secant. So in that case, this one becomes tan squared of x. This is 1 minus sec squared of x. And because we have a Pythagorean identity for trigonometric functions in terms of tan and secant, we also have one in terms of cotangent and cosecant. So now we have the analog in our case, which is coth squared equals 1 plus cosec squared of x. So they take a little bit of getting used to, right? You're probably going to have to refer back to your notes quite a bit when you're working with these things. So now we have a good idea of hopefully what these things look like, and you know, some general properties about these functions, how they can be mixed and matched to form the other functions. So of course, this is a calculus lecture. The next thing we want to do is figure out what its derivatives are. And the real beauty here is that the derivatives are fairly easy. Again, look at sinh and cosh. They might have you know, a new way of writing them, sin(h) of x or cosh of x. That's kind of new, but that's just a placeholder. All they are is exponential functions. And you know, based on the previous few lectures, taking derivatives of exponential functions and even integrals of them is awesomely easy. So let me lead by example. Let's do the derivative of sinh of x. So d dx of sinh of x. Well, of course, sinh is just a placeholder, so we should actually put in what this function actually is. And what we can see here is this is going to, the first term is going to differentiate into itself. So I get e to the x again. The second term, the minus comes out from applying the chain rule to e to the minus x. So mixing that with the minus that was already there gives me a plus e to the minus x. And the over 2 never changed. So what did I get? I got cosh of x. So sinh of x differentiates into cosh of x in the same way that sine of x differentiates into cos of x. So from now on, just like what I did with the identities, I'll start listing the properties. Again, you can prove them just using those exponentials. You can just follow exactly what I did right here. So d dx of sinh of x is equal to cosh of x. Well, then obviously the next logical thing for us to look at is what is the derivative of cosh of x? Now, here's where things get tricky. And here's where things get very, very confusing, especially for me when I'm going back and forth between regular trigonometric and hyperbolic trigonometric. And this is the tricky piece. In regular trigonometry, cosine differentiates into negative sine. In hyperbolic trigonometry, the cosh differentiates into sinh. I guarantee you, you will forget this, right? You will accidentally put a minus on this, and then the answers for whatever it is that you're working on will end up being incorrect, and you will never be, it will take you so long to figure out why. This is the most annoying aspect of hyperbolic functions. is that you have this property that cosh differentiates into sinh, not negative sinh. But nonetheless, after that, things sort of follow in a nice way. So if you take the derivative of tanh, in this case, you get sech squared, just like how you would get secant squared if you differentiate tan. How about if we differentiate coth, hyperbolic cotangent? In this case, you get negative cosecant hyperbolic squared. Sorry, I forgot the squared. If you take the derivative of sech, in this case, you get minus sech of x, tanh of x. And luckily for me, I always forget what these are with regular trigonometry, so I don't get confused too much. I usually have to look these up every time I use them. So I would love to give you some reminder of what the derivative of sech is, but honestly, that's been lost in my head. I look it up every time I need to use it again. So these are regular, just regular properties as far as I'm concerned that we can refer back to as we need them. And here you get cosecant, hyperbolic cosecant times hyperbolic tangent. So these are really, really nice, pretty properties. And if you wanted to, you could so easily prove these things. And I highly recommend it, right? You can either use the definition of each one of these functions in terms of the exponentials, or you can just use properties 1 and 2 for cosh and sinh. And then just like what you would do in regular trigonometry, you would use like the quotient rule, for example, to prove all of the rest of them. So, two methods that can be used to arrive at exactly the same conclusion. Now, just like with derivatives, we can undo these things. We can ask ourselves, what are the antiderivatives as well? So let's go ahead and put those in. Basically, we're just going to be undoing the table above us. So I'm not going to start with an example. I'm just going to give you a list of properties, and then we'll look at a few examples to round off this lecture where we've learned all of these new functions. Now we have some new tools at our disposal and some new functions to play with. So the first one is if you ask for the antiderivative of sinh of x, this is given by cosh of x. And that comes from the fact that cosh of x differentiates into sinh. Similarly, if I ask you for the antiderivative of cosh of x, this is equal to sinh of x, no negatives, so be careful. And we can do this for all of them. So similarly, if you have sech squared of x dx, this is tanh of x. If you have cosech squared of x, this is equal to coth of x plus c. Sorry, there's a minus in there. I got excited. This is minus coth of x plus c. If you have sech times tanh dx. All right, so I'm basically just undoing all of the formulas that are above, right? So I'm not putting anything new in there. I'm not giving you the antiderivative of tanh. I'm just throwing up some nice formulas that you can refer back to as you see fit. And it doesn't require you to do a whole lot of thinking and figuring out, okay, am I taking the antiderivative of this thing? Is it this piece? Here, it's just nicely sort of laid out for everyone. So the last one here, hyperbolic cosecant times, hyperbolic cotangent. And in this case, it's hyperbolic negative the hyperbolic of cosecant plus c, right? And so never forget the plus c, right? We can never forget that because we remember the definition of an indefinite integral is a set of all possible antiderivatives, not just one single one, it's any value of c. Okay, let's close this off with a few examples just so we can illustrate the things that we've learned in lecture today. So the first one is I want you to take the derivative with respect to t of tanh of square root of 1 plus t squared. So I threw you a curveball right off the bat. I've been talking about derivatives with respect to x all day, but again, this is something we can anticipate. This is something we can work with, right? Because x is just a placeholder. It means, whatever the independent variable is. Here, you can just replace all the t's with x's, and life is not so bad. The hardest part about this is that it's a chain rule application, right? The outer function is the hyperbolic tangent. The inner function is the square root of 1 plus t squared. So then the chain rule tells us we get sec squared of the inner function, and then times the derivative of the inner function itself. And in this case, we are going to get, again, this can be thought of as a chain rule application. And so here we get 1 over 2 times the square root of 1 plus t squared, and then multiplied by the derivative of 1 plus t squared, which in our case is going to be 2t. That's going to cancel the 2 that's down there. I like to put all the trigonometric or hyperbolic, trigonometric, exponential, everything. I like to put that on the end. I put all my polynomial terms on the front. So I get t over the square root of 1 plus t squared, sec squared 1 plus t squared. Right, so this is something that you should be used to, right? You're used to using the chain rule. The only thing new here was that you had a tangent and a sec in there. But, we can recall those properties. It's not too bad, right? I don't think I'm asking too much of you to take this derivative. Okay, how about if I have the integral of hyperbolic cotangent of 5x dx? Well, let me first remind myself, what is the hyperbolic cotangent? This is, this is cosh of 5x divided by sinh of 5x dx. And here, I'm going to make a little note off to the side. I'm going to have to do a little substitution. So I'm going to say let u equal to sinh of 5x. Sorry, let's get rid of that. Now, du is equal to, so a chain rule, the 5 is going to come out here. So I'm going to do it all in one step. 5 cosh 5x dx. I can see I've got a cosh 5x and a dx there. I need to divide off the 5 on both sides. And so this will give me the 1/5 coming from dividing off the 5 here. And the integral of 1 over u du, which from 3 video lectures ago, we saw that this is equal to the natural logarithm of the absolute value of u. And then don't forget that plus c, which again, we're not asked for a solution in terms of u. So we back substitute and we get the following. Beautiful, isn't it? Let me show you another cool one. Let me show you how you can use those identities. So how about if I ask you to find the definite integral from 0 to 1 of sinh squared x dx? Okay, so sinh squared is a huge pain. So we don't exactly have, if you try to substitute for this, you're basically going to try and substitute for sinh, but then your derivative is cosh, and that's not going to come out, and you're still stuck with an extra sinh. So what are you going to do? You're going to use an identity. You're going to back substitute for sinh squared. So let me go back for a second. Let's look at the identities. We can see that identity number 5 here turns a sinh squared into a cosh of 2x, plus some extra constants, but that doesn't really matter to us. So let's do that. So now I'm not changing the variable, so there's no substitution here. I'm using an identity. Sinh squared is the same as cosh of 2x minus 1 divided by 2 dx. So let me pull out the 1/2, and I get the integral of cosh of 2x minus 1 dx. If you'd like to, you can do a substitution for cosh of 2x, but I'll go ahead and just give it to you. You can substitute for 2x if that makes you more comfortable. But in this case, you get sinh of 2x divided by 2. And the the 1 integrates up to x. And here we're running from 0 to 1. And in this case, so if you're going to put this in, you're going to get a nice sinh of 2 divided by 4 minus 1/2. And the lower bound at 0 disappears. In this case, this is just a number, right? If you want to put this into your calculator, you can just use the proper definition of sinh, e to the x minus e to the minus x divided by 2. You substitute x equal to 2 in there. If you do that, you get 0. What do I have here? 0.4, sorry. 0.0672. I don't know. It's a number, right? It's just a number. The point is how we got there. Okay, let me give you one more example here. And this is going to look like a really ugly function until we remind ourselves it's, we just need to use the definition of sinh here. So maybe I give you an integral from 0 to the natural logarithm of 2 of 4 e to the x sinh of x dx. So I look at that and I go, that is brutal, right? This is a trigonometric function, or a hyperbolic trigonometric function multiplied by an exponential. But then a little alarm bell goes off in my head and reminds me, actually, the hyperbolic trigonometric functions, they're just exponentials too. So maybe I should just put in the proper form of sinh of x. I don't have to do anything fancy here. So in fact, this can be written as this. And now I've got everything in terms of exponentials, nothing fancy. And so if I expand this whole thing out, I'm going to get, in this case, just 2 e to the x, e to the 2x minus 2, because I get e to the x multiplied against e to the minus x here. So that's going to give me 1. And so then just the 4 divided by 2, that's going to leave me with the 2 in here. So maybe some fast algebra for everybody, but nothing too weighty. So in this case now, we can find some antiderivatives. The first function, the antiderivative is e to the 2x, because you're just dividing off that 2 coming from differentiating the e to the 2x term. And you get 2 minus x, 0 to ln of 2. And we can actually simplify this slightly. 2 ln of 2. So that's at the upper bound. Let's do the lower bound. 2 times 0 minus 2 times 0. So here, the reason I wanted to do this is so that I could show you that the exponential terms are actually going to simplify quite a bit. There shouldn't be a single e left in your answer, because we can use the fact that this is e to the ln of 4, 2 to the power of 2, minus 2 ln of 2, and then minus 1. That's the e to the 0 part right here. So this gives me 4 minus 2 ln 2 minus 1, which is 3 minus 2 ln of 2. So things simplified quite a bit, right? I'm still left with the natural logarithm of 2 in there, but whatever. And if you wanted to, you could find out that this is equal to 1.6137. But that's just after putting it into your calculator. Okay, so just in summary, what was it that we saw so far in this video lecture? Well, we introduced a whole new class or set of functions, and that is the hyperbolic trigonometric functions. And so you can kind of ask yourself, why are these things called trigonometric functions? They're not really trigonometric functions, they're just exponentials. Well, there's a much deeper mathematical reason, and this is because they are related to what's called hyperbolic geometry. That's where the hyperbolic component comes from, which we're not going to get into too much, or if at all in this class. But there's a more sort of intuitive method of thinking about this. They act and behave, they look a lot like the usual trigonometric functions that we've already seen, sine and cosine, tan and whatnot. They're defined in all the same ways. They have similar identities. They're not exact, but that's because they're not exactly the same functions. They have similar derivative properties. Again, not exact because they're not the same functions. And they have similar integration properties. So there's this sort of intuitive aspect of why we call them trigonometric functions, because they sort of behave like we expect the trigonometric functions would. And then, of course, there's a much deeper meaning coming from much more complex geometry and mathematics, which is, again, this relation to angles in hyperbolic geometry. Okay, in the next lecture, we're going to talk about the inverse functions of each of these hyperbolic trigonometric functions.